All right, welcome back everyone. We'll get started to look at some different operations using our vectors, right? And so in section 12.2, which we had finished last, it was just dealing with introduction to vectors, right? Some quick additions. I'm not sure if we actually did an addition where we just add component-wise. We found the magnitude or the length of a vector. Now getting into a little bit more interesting and points, or probably actions that we'll go through with these vectors. Let's take a time to look at section 12.3. Okay, so let's start to share the document. Okay, so we had our introduction to vectors previously, right? Suppose we have our vectors, again, whether they be two-dimensional or three-dimensional, we can identify those, and they give the notation a sub 1, a sub 2, a sub 3, and vector b, right? Those bend brackets to identify we have these components. So it's not just a point in space, but this vector, right? A magnitude or direction that we're facing. We're going this far in the x direction, this far in the y, this far in the z, kind of that arrow pointing out, trying to get my finger, here we go, right? In space. And we can measure that magnitude by computing those quantities, okay? All right. So if we have these two vectors, right, we can do an addition, right, adding component-wise to get that new vector, subtraction. We can multiply by a scalar, distribute some constant through to elongate or to compress that vector's length, okay? And so the dot product or the scalar product or the inner product, just different names for this action. And we'll see why it's called a scalar product in a second. But the dot product, the scalar product, the inner product of two vectors is computed as the following. So if I'm taking A and this kind of dot with B, dotting these two vectors, so not necessarily a simple multiplication dot, just trying to make it a little bit more emboldened. This dot product between two vectors, right? These objects that have a magnitude direction. How we compute is we multiply component-wise and add those results. Right, so we multiply component-wise, the x coordinates, or components, just say, sorry, y components, z components, whatever they might be, multiply, and then add those results. Okay, so let me put that in language. Multiply component-wise and add the results. And so, right, what an important result might be, notice here, notice our result is a scalar, right? Hence a scalar product is a scalar, right? Just a numerical constant, if you will, many times. Value. Okay. Hence scalar product, because once we compute, we just get a number out of it. So for example, well, if we want to compute the dot product, taking, let's say, 3, -1, 5, dotted with 2, 4, -2. Okay. So if I'm going to compute that dot product, this is like our A vector, B vector, dotting those together, that dot product, 3 times 2 plus -1 times 4 plus 5 times -2. Again, I can color coordinate those. Try to make those match up a little better. Okay. But multiplying, 3 times 2 is 6. -1 times 4 minus 4. 5 times -2 minus 10. 6 minus 4, 2. 2 minus 10, -8. Double check my arithmetic there. But the result of the dot product can be positive. It can be negative. It can be 0. But it should never be undefined, right? As long as we have all real number values, components within those vectors, we should be able to compute the product and sum and get a real number result. Okay. So there's that dot product, positive, negative, right? So then some properties of that dot product. I'm going to start off with a interesting and important property. Again, this is going to be on page 847 of our text, the 8th edition of our calculus, Stewart, okay, with early transcendentals. Given we have these vectors, the first property we have is that if I take the dot product of a vector with itself, that's going to be equal to the magnitude of that vector squared. Okay? That length of the vector squared. Because again, think about that length, that magnitude calculation, the square root of a sub 1 squared plus b sub 1, or plus a sub 2 squared plus a sub 3 squared, those components squared, right? When I dot something with itself, a1 times a1 plus a2 times a2 plus a3 times a3, a1 squared plus a2 squared plus a3 squared, those components squared, right? We just don't have the square root feature, so there's our magnitude being squared. Okay, next up, just kind of copying these down real quick, we have the fact that the dot product is commutative. Since we're multiplying and multiplication with real numbers is commutative, the dot product should be commutative. Okay. Then we have something like a distribution. If you have A dotted with the sum of two vectors, then to some degree, we could distribute, I'm sorry, this is C right there, sorry. We can distribute that dot product through that sum. So the kind of distributed property. Then we have a scalar multiplying, right? So that's just scalar multiplication. That's a constant. That's multiplying a vector. And if we're dotting that with some secondary vector B, this kind of transitive property that I can factor that constant out completely, do the dot product first, then multiply it in, right? Or likewise, I can imagine attaching that constant, that scalar multiplication to the second vector instead. Is not going to distribute. It's not a distribution here. It's which vector, which result will attach that constant to. So this is kind of like our transitive property with scalar multiplication. Okay. And then lastly, if we have the zero vector, that's going to be 0. Okay. And again, going back to our commutative property, the 0 vector times anything, or anything times a 0 vector is going to give you a 0 result. All right, so our 0 vector means just all the components, all are 0. And remember, for the dot product, we're getting a scalar result, a numerical result, not another vector as a solution. It's just zeroing out that component. Okay. And so now, with some diagrams in the text, going back to some of our work with trigonometry, okay, and I'll let you check out that discussion. But then another important use of our dot product, okay, of that dot product is to find the angle between two vectors. Okay, slide this up. So again, this can be in 2 space or 3 space. I'll do it in 2 dimensions just to make the visualization a little bit easier. Okay, but suppose we had 2 vectors, vector A and vector B. Let's just put like so, right? And again, with a vector, it doesn't have a set location, it doesn't have a set place to start. Okay, vectors just have a magnitude, length, and a direction. So I can take those vectors and slide them around our coordinate system of our see fit and still be equivalent, right? But if we're to do so, as best I can, to make it so that their tails coincided, right? So if I did a little bit of shift to get their tails to coincide, we might want to identify how wide of an angle is between those 2 vectors. And again, this can be extended to 3 dimensions. So imagine kind of swooping that around, having these vectors pointing out of this towards the board, towards, space, whatever it might be. But again, still finding kind of some plane in which we can measure the angle between those 2 vectors. Okay. And so the dot product is a means for doing so. And this brings in, right, kind of, if you imagine drawing in a triangle and so on, using the magnitudes of these vectors. And on page 848, there's some work in identifying, okay? So I'm going to leave that for your review. to look at, page 848, has a diagram and proof for this calculation, okay? So you're not just taking my word for it, but it is verified. And again, you probably search online for a proof of this as well, a discussion there. I might try to search for you as well. But given these two vectors, okay, given two vectors, A and B are generic vectors to start. Then the cosine of the angle between them is equal to that vector A dotted with B, that dot product, divided by the product of their magnitudes. Okay. Dot product of A and B. And this is just the multiplication, because when we look at the length, that's a scalar value, a numerical value, multiplication of the lengths or magnitudes of each vector. And then that cosine theta, theta is our angle between those vectors A and B. Right? And so if we want to actually find that angle, it's just going to be that inverse cosine of that calculation. Right? And we can find that measurement, how far between those two vectors. And so this can help us out in a couple instances, right? In some cases, when we start to calculate here, we might start to see some of our special forms, our known angles, right? This calculation might come out to be that √2/2, 1/2, √3/2. Some of those come out to +1, 0, okay? So that might come up, or might come up some random decimal that we'd have to go into our calculator and find that radian measure, remember, of that angle theta, and we can convert it into degrees if we so desired. But just remember, whenever we do these, we're talking about radians, okay, as we start, okay? Theta measured in radians. Remember that, okay? All right. And so again, given two vectors, we can compute the angle between them, all right? And so then, in particular, a special case, we have the case when that cosine theta is equal to 0, right? Meaning, when I look at that dot product, as long as those don't have magnitude 0, right? They're not the 0 vector, that's equal to 0. So when that dot product is 0, the cosine is equal to 0. That means the angle theta, what angle has a cosine equal to 0? Think about your graphing. Think about your special unit circle. When that angle theta is pi over 2, 90 degrees. A right angle, right? So in this case, when that dot product 0, that angle between them is going to be 90 degrees. The two vectors, right, form a right angle. The vectors are perpendicular to each other, right? Right angle, they're perpendicular, or what language I'm trying to work towards, these vectors are orthogonal. Okay. So there's our new language. Orthogonal. Okay. When those two vectors form a right angle, their dot product is 0. We'll say that those vectors are orthogonal. Okay. So let me leave it at that introduction to the dot product and this particular calculation. We'll still spend a little bit more time in this section 12.3 working with this angle between two vectors, but just getting us started here. All right, so this set of notes, this recording will be on the Canvas site for your review. And definitely, if you have any questions, please let me know. We'll be continuing with this work in the next lecture as well. So stay tuned. All right, take care. Stop sharing here. If you have any questions, let me know. Otherwise, see you soon.